Okay, right, we're ready to get started again. This is the last one in this room for the day, so I'll welcome Jordi up here.
Works? Yeah, here we go. Good afternoon, everybody. I'm Jordi Baylina. I'm the technical lead of IDEN3 project. Have a lot of things to announce today, some of them very interesting, so I will ask you to stay tuned because there are important things to explain today. So, well, let's start. This is the first plane that actually flew, the Bright's brother in North Carolina. Let's see if I get. You see here a nice flight, controlled flight. It works. This actually was the first engine that this airplane had. You may not realize, but this looks very much like an Ethereum blockchain. In many years, aviation was improving and getting better. But we saw, the people saw that at some point there were limitations in this aviation. And if you wanted to go fast, if you wanted to do transatlantic flights, you need to improve. You need to make an important change on that. At that point, we had this technology. This is the first turbine, the gas turbine, that was invented. So we had the technology. And the idea was to try to put this engine in the plane. But as you can imagine, if you put this turbine in one of those old planes, it will not work at all. Mainly, we had to go to the design, to the full design, and redesign the full planes and make them more robust so that we can plug this kind of turbine. Well, why I explain you this story? Because right now we are in a very similar situation in the blockchain space. We have a nice blockchains. We can do smart contracts. We can do many things on them. But we need to go fast. We need to scale. We need to go faster. And actually, we have the turbine. We have, right now, we see that all the rollup with all this zero knowledge, with all these succinct proof of computations more than zero knowledge, we can solve that. So we get the engine. But if we plug this engine to this to our blockchain, it will not work. Why? Because it's not only about verifying transactions. There are a lot of things that needs to be redesigned. Nothing that cannot be done, but a lot of work and a lot of things that needs to be done. Just think for a moment, 2,000 transactions per second. You cannot process that in a Raspberry Pi or even in a normal desktop place. An operator that's taking these transactions first needs to have infrastructure to receive 2,000 transactions per second. It needs to get these transactions, it needs to verify all the signatures, for example. You need to store them. Imagine the backlog, the backpool that will have this infrastructure. We need to select which transactions needs to be included in each block or in each new mine. This optimization problem is not about 100 transactions or that we may do right now or 200 transactions. It's with thousands of transactions that we need to do this process. Once we have those transactions, we need actually to process them, to calculate all these states, to compute all new hash roots of the state. And then, after that, we need to compute a witness. That's something that we will talk later. That's one of the bottlenecks that we had and that we solved, and I want to talk in this presentation. But then we need to compute the proof. The proof is actually this innovation that we saw. Well, it's a hard computing problem, but solvable. Okay, but it's not only about the proof, it's about everything that's going with that. And not only that, okay, we get the proof, we put it on chain, but then we need explorers. We need transaction explorers, blockchain explorers, Etherscans like. Well, when you have 2,000 transactions per second going on continuously, this is the technology that you need, for example, to write a block explorer that's handling all this information is not of use. We can do it, we have technology, but this needs to be built. So that's what I want to give you awareness of what means scalability. It's not only about computing proofs. So, well, let's first, maybe from the people that don't know, but I'm going to go very quick, but mainly what's a rollup. Here, a rollup, what we are taking advantage is, well, in a normal blockchain, what we have mainly is we have a state. You can imagine, for example, the balances of all the accounts. We want to process a single transaction, and then we compute a new state, mainly with a couple of balances switched to some of them. One of those will be subtracted, another we added. That's mainly what we are doing. And this transaction processor, if we see a very simple, if we imagine, for example, a very simple blockchain that just process one transaction per block, well, this process of computing the new state, this needs to be done for all the computers in the network. This is what we call the verification part. Okay? So mainly what we are doing in a rollup is instead that everybody runs exactly the same process of validating a transaction, what we do is we have one operator or one set of operators, like a miner, if you want, that will process that, will process it, and will generate also a proof. We will compute a huge proof. Well, it's a huge, difficult to compute proof, a highly computational power proof, and then the remaining people in the blockchain will be able to validate this transaction very easy. But of course, we are not going to do it with a single transaction. We are going to do it with many transactions. We will have a block that processes 2,000 transactions or whatever number, a huge number of transactions. An operator with a big cluster will process the transactions, will compute this proof using very expensive computer power, and with this proof, then everybody in the network will be able to validate these 2,000 transactions in a time constant, or something that's very succinct, something that's very fast. And this is what allows us to scale. Okay, so this is mainly what's a rollup. And what we have inside this transaction, just as an idea, well, what we do mainly is we need to verify the signature, we need to verify that we have enough funds so that we cannot overspend. We need to do normal validation that we need to do in a normal transaction. But of course, we need to do it in huge blocks, in a lot of transactions. So how do we compute these proofs? What's the way to compute this proof? Actually, there is a huge and important machinery, cryptographic machinery, that allows us to build that. Okay? But this proof, actually, this computation, if you want, it can be understood as a function. It's a function, a mathematical function that actually has two inputs, mainly the state and the transactions that we want to process, and as an output, we have the new state. And you can think that as a function, as a mathematical function. So these systems, for succinctness, as an input, you need to tell them which is this function. What do you want to compute? Okay? This is a white paper, the Ethereum white paper. And very in the beginning, you see here this function. It's a very known function in any blockchain. Okay? So, and this is a deterministic function. This is a function that, given an input, you have an exact output. If you have different outputs, you will have a problem of consensus there. Okay? So you have given an input, you have exactly an output. So it's a mathematical, a perfectly defined function on that. Okay? And these systems to compute this, if I want to compute the output of this function, the result of this function given an input, and I want to compute a proof that the output actually is the one with the input, but in a succinct manner, what this cryptographic system requires us? Well, it requires us to tell them this function. And how we have to tell them? Well, we need to use one thing that's called R1CS constraint system. That's mainly, let's put an example of what's this constraint system. Here we have a function. We are not putting this validation, this state transition function. We are putting a more simple example so that we can understand how this works. So mainly, imagine a function that's something like that. You have a function that depends on 3 inputs, S1, S2, S3, and the result is going to be S4, okay? And well, you see here S1 to the 5 plus S1 to the 2 times S2 plus S2, S3, okay? So the way is that we need to put a constraint. Mainly, we need to put a relationship between the output and the input. A normal way of doing that would be this. Just for example, just saying that S4 must be this. We are done. Okay? The problem is that this is not R1CS. It's not an R1CS. Why? Because in this constraint, there is more than one multiplication. Okay? So we need to convert mathematically this in something that's a constraint system that has only one multiplication per constraint. So we do mainly what we do is this trick. So we create new intermediary values, intermediary signals if you want. For example, we create this S5. We say that S5 is S2 times S3. Then we say that S6 is S1, S2. S7 is S1, S1. S8 is S7, S7. And S4 is S1, well, this. And you see that S4 actually holds. And if you hold all this constraint system, you actually will hold the first statement. And the nice thing of this is that if you see here, there is only one multiplication per constraint. That's actually what an R1CS is. An R1CS, mainly what we are doing is doing a relationship of a function of the output of the function, given an input of a function that must hold, and we need to convert that. And this is the input of this cryptographic machinery that allows to compute the proof that the output is this input, but without having to execute to compute all this function altogether. Another way to see this is with what we call it an arithmetic circuit. Arithmetic circuit you see here is exactly the same. Just multiply, compute these new things, but we see it in this nice diagram that's called an arithmetic circuit. Okay, so when we are talking about a circuit, when we are talking about a deterministic program, when we are talking about a predicate, when we are talking about, well, there are different names for that. We are always talking about the same. We are talking about a function that's given an output. So given an input, you compute an output, and you have the relationship between this and this. And this constraint system, in a standardized format, this is what we can send to the cryptography, to the machinery that allows to compute this proof. Okay? Let's see how this circuit would be, for example, in circom. For any of you that don't know, circom is a language that we created in IDEN 3. It's a DSL language that allows us to create these functions, to create these circuits, and allows us to convert. You just create a circuit like this, and then it will convert automatically to this constraints system. Okay? So here you see we define the signals, in this case the 3 inputs, S1, S2, S3, an output S4, 3 intermediary values, and then you see here something that goes with a double arrow. Well, this means 2 things. First is that there is a constraint that S5 must be S2 times S3, but it also explains how to compute this intermediary signal. Why? Because when we want to compute a proof, we need two things. We need the constraint system, but we also need to compute all these intermediary values. This is what we call the witness computation or the witness calculation. We need to do this calculus. So when we are talking about witness computation or witness calculation, we are talking about mainly computing the function and computing all these intermediary values in order to compute the function. If you take these intermediary values, of course, they will fulfill the constraint system. Okay? So in circom, mainly what it does, when we have a circuit like that, we have two outputs. One is the constraint system. So given a circuit, you will have a constraint system. The circuit of here, you will have 5. The output is going to be a constraint system of 5 constraint systems. And the circom also generates what we call a witness computation. That is, when you give an input, so a witness computation is a normal program, can be in WASM, C, or it's a program or a JavaScript. It's a program that you give 3 inputs, and it will compute all the witness. It will compute all the intermediary signals plus the output. Okay? And this is, with this, with the result of this, you can then apply all the cryptography machinery, all the zkSNARKs, in order to compute these proofs. Okay? But to go in there, so this is important. Okay? So let's put another example of a circuit. Imagine a NAND gate. NAND gate has 2 inputs, an output. Interesting thing of a NAND gate, well, here we have the truth table. You see that if S1 or S2 is 0, the result is 1. But if S1 and S2 both are 1s, the result is 0. Okay? What's the constraint system that fulfills this output? Well, you can see here, S3 is 1 minus S1, S2. Here we are working in binary fields. Probably, in a normal SNARK, we will have to add some other constraints in order to guarantee that. But for these examples, it works. In the right side, we see the circum. How would you write that? You see that you have 2 inputs, 1 output, and then you just assign S3, and you will get this. Just let me put another example. For example, what happens when you want to do a division? And this is more advanced topic, but I think it's interesting here. Okay, you cannot create a node with just multiplications. So here we do a trick. You see, well, instead of telling that A out divided by B, A divided by B is out, what we say is that division by B, we put it in the other side of the equation, and then we say that the out times B must be 8. Okay? How we would write that in circom? Well, here we use a single arrow just to compute. So here we are telling how we compute this signal, but then we are adding by hand the constraint that we want to add. And this is one of the cool things of circom that allows us to build this. This can be very insecure. You know, single arrow, if somebody is listening to this, single arrow should not be used in circom unless you know exactly what you are doing. But if you know what you're doing, it allows to do things like this. For example, a normal division. Okay, so here is, you see the idea of how how creating a circuit works. Okay? Okay, we have a NAND. But let's do a more complex circuit right now. Let's put 2 NANDs. Well, we join them together. Okay? So, well, here we have the old NAND, and here we can do in circom is just join them together. Create these 2 NANDs. We instantiate here. You see the component G1, component G2. We instantiate them, and we connect all the signals, the output. So we do all the connections to the signals. So this composition, this allows us to composite. And there is one interesting rule in electronics. That's if you are able to build a NAND and you are able to use as many NANDs as you want, means that you can build anything. Anything, any function you want, it can be built with that. So this is important. That's why it is important, this NAND. So Okay, let's build circuits. We start with a small component, we put them together, we create bigger components, we put them together, we create bigger components, and so on. So we can build very, very big circuits. Actually, we have this circom lib that's a set of basic circuits that we can use for in many applications. Here we have hash functions, we have Merkle trees, we have multiplexers, we have comparators, we have a curve, an elliptic curve that we can work inside the thing. We can do anything that we want. We can do any computation that we want in this function, in this circuit. And all this is already packed as a library with the small pieces that you can build bigger pieces, and you end up having a rollup. Well, you just create a transaction like this, you create a component that's a transaction, you put a lot of these components, and you create a full rollup. Of course, with thousands, well, actually with millions of constraints out of there. But we have to build this DSL. This is very much like building electronics. This is very much like putting components together with the small components. So this is what we are doing here. Okay? So circom, now that we're working on circom, I want to just highlight some of the new features that we are working for in circom, just to know. One of the things is, for example, one of the bottlenecks that we have is this witness computation. When you have millions of constraints, you have circuits that are huge, very, very big. Computing this witness is, it takes a long time. It's very expensive. So we need to optimize that. So in this case, circom, the program that computes this witness right now in the new version will be a C++. We have built also an assembly library that works with finite field. That's quite fast. And when we plug them together, it goes really fast. Just to mention here is that, well, right now it works in C++. It also will work, we are working on that, but we will work in WASM. So we will generate directly WASM code to generate this witness. Important to mention also that this computation of the witness is going to be in parallel. So if you have a multi-thread computer, you will be able to use all of them. We'll talk a little bit more later on that. Well, right now you can build big circuits. Some of them maybe could take a while, but actually it's possible. We have to tune a lot the compiler in order to be able to build these circuits. Right now it's also interesting that works with any corp, not only with the BN128, it works with zkSNARK corp and MNT corps and other any corp that you can imagine. And also interesting is that all this circom lib is audited. It has been also audited. This is thank you to the Ethereum Foundation for doing a lot of this work. There is still a lot of work in progress. We are trying to stabilize a definition, functionality of circom. We have freezing a paper so that we can freeze this and more convert this language as a reference language and having this version on that. We are also working in a faster Rust implementation of this language. And yeah, we need to improve also, well, create a lot of more, we need to amplify, create more circom lib, more libraries and more circuits to work on that. Also, it's important that with circom, it should be able, we will work on that, to plug not only to zkSNARKs, but for example, we want to plug it in Plunk, or we want to plug it in Bulletproofs, or any other cryptography machine that allows to compute these zero-knowledge proofs. Okay, so let's go back to the rollup example. Right now, we have a circuit that, as you can see here, it processes one transaction after the other. Okay, so this is, well, if you see the witness computation, and I'm going to focus now especially to the optimization of the witness computation for a rollup circuit. if you see the witness, well, here, this can be 2,000 transactions. And if you do it just in a naive way, the problem that we have is we have a dependency problem. So mainly, in order to process the transaction 2, you need to process first the transaction 1, and in order to process transaction 3, you need to process the transaction 2. So we cannot parallelize that because we have this dependency. So how we fix that? Well, in the case of a circuit, it's quite easy. We just code them. We supply. We do a kind of trick here. We just supply as an input what should be there, and then we just add a constraint that this input should be the output. Okay? So if we do this, actually, we can compute all these witnesses in parallel. Well, actually, we didn't solve the problem. What we did is we just moved the problem to the input to this circuit. But at least from the witness computation point of view, if we accept that we have these inputs, we are already parallelized. And this is, believe me, this is an important improvement on that. So how we compute all the inputs here? How to compute these intermediary states? These intermediary states, for many of you that don't know, and this is a little bit more advanced, but mainly are siblings of a Merkle tree. We have a state that we want to process in each transaction, and most of the time it spends just by computing, just going back and forth in a Merkle tree just to restore a state, compute new state, and compute the new root on that. So mainly when we are inserting something, for example, when we want to modify some leaf in the state, like this dark blue here, well, we need to compute the hash function. So we need to compute a new hash function for the fathers of this until we compute a last function here. So when we build that is instead of actually doing the computation, we just take note. We just say that we have a dependency. In order to compute this, you need this. In order to compute this, you will need this hash. In order to compute the first, you need this hash. And this is the arrows that you see here. When you process the next transaction, actually, well, you have exactly the dependencies of this field, but you see in the second line, you have also the dependency of this one, that this one actually is exactly this one. So you can build this dependency graph. When you have a third transaction, you have exactly the same, but you have this other dependency here. So if we analyze what's the dependency of the last one, here you see that, well, it do not depend on the number of transactions, but depends only on the number of the levels. So if we want to build the siblings, we can parallelize also that very much. So this allows to compute the witness of the transactions and to process transactions in a way that's not linear, it's logarithmic if you have enough parallel computation on that. So you can parallelize that very much. So that's it. And now the announcement that I promised at the beginning of the talk. Today, we have been working a lot, but today we just launched a first version of rollup in testnet. So you can connect here, and you can start doing your transactions. You can start testing that. It's a command line interface, very primitive. For sure, it's going to appear a lot of bugs. So do not just, it's not even a beta. It's just, but right now, we have all the pieces put it together. That works. And of course, now still a lot of work to do in order to maybe optimize some of these pieces, making them better, maybe some of them replacing them. It's still auditing them. And we hope that at some point, this will be launched in the mainnet. But right now, we have all these pieces together, and we are working. And we are inviting to anybody that wants to connect, please go here. We have opened also a Telegram group for helping the people. So if you want to connect, here it is. This is the QR code of of this. It's not the trusted setup. It's not the trust community one. So if anybody wants to connect to trust community, just please later, just ask me. But you can connect here. And that's it. So guys, let's go scale.
Wait, if anyone has any questions, you can raise your hand.
Don't know if there are any questions.
Yeah.
I have no idea how much I'm in time.
So what are you building basically is just a DSL which translates down to, currently you are using libsnark, right?
Sorry?
I mean, as your backend, you are using libsnark.
No, we are using, right now, we are using SNARK.js, and we are using, there is a connection with Bellman, and it can be connected to libsnark if you want. Actually, the idea is that the output should be transparent to any of those. But right now, it's mostly, we also develop SNARK.js and WebSNARK, which is a native implementation in WebAssembly that works very fast, especially in the browser. If you want to use libsnark in the browser, it's quite hard.
But the whole goal is that of the project is to have this circom language, which will translate down to whatever is the backend?
Yeah, it's to work on another backend. We also develop, this SNARK.js, but I have not been talking about the backends. I've been talking about just the circom here.
Okay.
But it should work to any backend.
And so you are very similar to O1 Labs Snarky,
Snarky is another language. It's similar to
OCaml.
circom. I think it's based in OCaml.
Yes.
On that.
I mean, just to put it like you are this like.
Yeah, there is like two kind of languages here, just to have an idea. In one side would be Snarky and circom that are more DSL kind language that are actually what it just connects components, as we saw, and you connect a lot of the components and you create that. And then there are other set of languages. Here we have Socrates, new Zinc, and some other languages like that that are more high-level languages. That the idea is that you should be able to write any with like a normal programming language, and the compiler will do the magic for you. These are more low level. This is you just design these components, you just connect them together, put it this way. So this is the two. Maybe in the future, the high level languages make a lot of sense, but I think that in the current state of the technology, these low level languages are very good, especially for auditing and for knowing exactly what you are doing, what constraints are you building. So I think the both are useful, and playing with both is a good thing.
And like which schemes do you support now?
Right now, there is, of course, a SNARK.js, because we built the SNARK.js, and that for sure.
Schemes like Grok, yes.
It's Growth 16. Mainly, the Growth 16 is the main that's most used. There is one, is OT, some Korean guys also, that it allows you to build a proof, a non-malleable proof. But the problem of this scheme is that you need to do some computations in G2. So this does not work very good in Ethereum, for example. But mainly, the interesting is that you can generate with SNARK.js, you can create a verifier for Ethereum, and it's a growth. There is also this BTV 14th, but it's like it makes no sense to use it. So it's growth 16 probably is what makes more sense. I hope that in the future, Plonk should be easy to port it, and there are many other schemas that are appearing that it's possible to port. Right. It's like this is the back. This is the front. It's another piece. This is not a cryptographic piece. The idea is you should be able to plug it.
So here. So like for this backend support, you say that your target is mainly SNARK.js, but later on you're adding. Yes. you just started to support something else.
Here, the big difference here is the difference and I think that's what makes a lot of difference probably with other languages, is that we are generating code. So we are not running. So most of the systems is that when you want to compute the computation, in some way you need to run the circuit in some way. You are not running any circom. We are just generating a code that...
Yes, but currently, like, the circom only, I mean, the full support is only for the libsnarks. Sorry, the SNARK.js.
Yeah, SNARK.js, and there is also a port to Bellman.
Full one already? Like, I can
I have not written that. I need to check, but I know that there is people that's using Bellman as a backend.
Oh, cool. Thank you.
Yeah, is there any more questions?
One question. So I saw on the website that you have ERC20 support for this rollup chain, for the side chain.
Yeah, it's here, so, ERC20.
And how long would it take to make this generic smart contract computation possible?
Well, it depends on the number of transactions. Right now, in I think it's 700 transactions in the chain, it takes like 1 minute. If we go to, but depending, but that could be a reference. But we believe that we can improve that a lot more.
Yeah, I not only mean like kind of like how many, what's the scale up, but can.
Yeah, one good parameter that you can think is 2,000 transactions. Okay, right now 10 minutes, like a Bitcoin schema. That's a good reference right now, but as I tell you, we are improving those numbers. There are other teams that are also working on this, and they are also improving. I don't know if you saw the last looping paper. They are also doing a great job in improving this proof generation, and we believe that we can go really low. So there is a lot of work, engineering work to low that, and I believe that's possible that in not many times we can have we can compute those proof in few seconds.
Yeah, but currently it cannot generate a generic smart contract in this transaction. It's like a custom-made ERC20 thing.
Yeah, this rollup is for transfers. Okay, so you can do transfers, and that's it. It's not a smart contract on that. In order to build a smart contract, you need to, this rollup, you need to have some reentrancy on there, because you need to verify something that inside, so a verifier inside the verifier. There are some projects like zkSNARK, or well, you would need some other corps. Actually, they are not implemented in the precompiled smart contracts on Ethereum right now, but they are planned to build on that. And with these reentrancy corps, you should be able to run anything you want inside the SNARKs, so you should be able to run smart contracts. But I think we are still a little bit far away. There are teams that are actually start working on that, but we are a little bit. I want to see first a rollup running full speed, and we'll see step by step.
Thanks.
Yeah, if there's any more questions.
Yeah. Okay. Well, thank you very much.
Thank you.